Hello, everyone. Last time we talked about tree traversal, and we have introduced three different traversal methods: pre-order, on-order, and post-order. So if you can understand the principle of these three traversal methods, then we can consider root, left subtree, and right subtree in the order of the sequence when we traverse this tree. On pre-order, we follow root first, and then all left and right subtrees. But remember, when you visit left subtrees, you also need to apply the order to visit left or right subtrees. For in order, our sequence will be left, root, and right, and for post order, we visit root in the last position. So the sequence will be left, right, and root. Okay, today we will extend this topic to introduce expression tree. Okay, so let's see this expression. If we have x plus y parentheses error 2, so if you consider this error is the differential of operators, so you can calculate something from the result of x plus y and 2. And then we have another parenthesis x minus 4, and we add these two results together. So this is what we call our expression. So let's, based on this expression, we can build a tree for this expression. For example, we have first parenthesis plus y. So we can write the operator as our root, and x and y as left and right child. So we have the first expression tree, x plus y, like this. Right? And then we have the result of x plus y arrow 2. Okay. So now we have two operand and one operator error. So we put error in the root of the tree, and the result of x plus y as left subtrees and 2 as the right child. Then we can just illustrate the expression tree of one parentheses on the left-hand side. Of course, we can use the tree for the second parenthesis, x minus 4, and x minus 4 divided by 3. So finally, we can combine these two parentheses together by the addition as the root, and we have the left parentheses and right parentheses. So this is what we call expression tree. Actually, you can draw any trees for the expression. Next, connect to the previous traversal method. Then we can build infix notation. So if we apply in order traversal to a tree and then we build the representation, then we can build something like this. Okay? So if we have x plus y divided by x plus 3, we can apply this one to infix notation. Okay, so let's see the three examples because we have three expression tree, but this three expression tree actually is like to the same expression x plus y divided by x plus 3. Okay, so let's see the first tree. Okay, so if we have x plus y and x plus 3, first one divided by the second one, then you will see actually this is the same to x plus y divided by x by 3. Because if we apply pre-order traversal, then you can see for pre-order, that means we visit root first, and then x and y. And for in-order notation, we visit left subtree, and then the root, and then the right subtree. So in this case, you can see because we apply in order traversal. So we visit that subtree first. So for divide left and right subtree, we visit left subtree first. And for this left subtree, we visit x first. And x plus y divided by x plus 3. So we have x plus y divided x plus 3. Okay, let's see the second tree. If we apply in order traversal, then remember we visit okay x plus y divided by x plus 3. So we put the root in the middle. Okay, so still we have x plus y divided x plus 3. We still have this blue expression. So let's see this tree. X plus 3 divided x plus 3. So in this equation you can see for these three different operations, actually if we apply in order traversal, then it reflects to the same blue expression. Okay, so in this case, we need parentheses. Okay, because if we don't have parentheses, then for these three trees, actually we can write the same expression. So next, let's see prefix notation. If we apply pre-order traversal, then we can obtain the prefix of this expression. Okay, so for prefix notation, once we apply pre-order traversal, then we visit root first, and then left subtrees, and then right subtrees. So for this expression, so we can see we have x plus y. So actually we have, if we apply prefix notation, then we will have plus x, y. And then this one, arrow 2, that means we have the prefix notation arrow x, arrow plus x, y, 2. And then we have the second part, minus x4. And here we have a group condition. So divide minus x4. And then these two combine together, and we have addition in front. Okay, so this gives us prefix notation. If you are very familiar with pre-order traversal, then maybe you can write this expression to prefix notation directly by yourself. And we also call this notation Polish notation because it's, the name is given after this Polish logician. Okay, however, if you cannot write prefix notation directly from the expression, actually you can draw the tree first and then convert the tree to prefix notation. So let's see this x plus y parentheses arrow 2, then we have x plus y arrow 2, and then we have x minus 4 divided by 3. So x minus 4 divided by 3, and then these two terms add together have a plus as the root. Once you draw this tree, then you can apply our previous pre-order traversal method. Okay, then you can have plus arrow plus xy 2 divided minus x4. Right? So that will make this question easier. If you cannot convert directly to the answer, then you can transform to the tree and then apply pre-order traversal to create the prefix notation. All right, so
let's take a practice.
Please apply prefix notation to see if we have any different concept in order or in fixed notation. So write down your answer on your paper about prefix notation, about these three trees.
All right, one extra point if you share your answer. Okay, please. Okay. Let's verify this answer by a prefix notation. Okay. So in this case, we have x plus y, so we need to write plus xy and plus x3 and divide in the first place. Okay, so this one is correct. And then we have y divided by x, so we have y divide yx, and then x plus, and then plus 3. Okay, so this one is good. And the last one, we have plus x3 and divide y and plus x. Okay, so this is very good. All right, so based on the answer, have you noticed something very important? Because for infix notation, once we have three different trees, but the answer is only one. So we cannot distinguish between the different trees. So that's the reason we need parentheses for this equation. But if we apply infix notation, then you can see for these three different trees, we will have three different expressions. Okay, so if we apply prefix notation, there will no ambiguities. Okay, that means we are not confused with the different trees by the same expression. If we apply prefix, then we will have three different trees for the answer. So that is the reason we don't need parentheses for prefix notation. Okay, lastly, let's see postfix notation if we apply post-order traversal. So we also call this reverse Polish notation. Okay, so we put the operator in the last position and we visit left and right subtree first. Okay, so let's see. For the same expression, here we have x, y plus, and then 2 error. Okay, and then we have x4 minus 3 division plus. Okay, so let's see our answer xy plus 2 error. This is the first term. And then for the second term, x4 minus 3, x4 minus 3 division, and then plus. Okay, so this is the direct transform from the expression to postfix notation. However, similarly, you can also transform the expression to the tree, and then you can apply post-order traversal to build postfix notation. All right, so that's the end of this section. So let's have a quick review of this section. Actually, we have introduced the universal address systems that how to represent a tree by its order. So we can have different names, different naming rules for different level of the node of the tree. So we call this universal address system. Once we can confirm the order of all node of the tree, and then we have introduced 3 different traversal methods. And then this traversal method can transform to 3 different notations to expressions. Okay, any question for this section? All right, if no questions, then let's jump to next section of spanning trees. Okay, so in this section, we will introduce what is a spanning tree, and we have different algorithms to discover the spanning tree, depth first search and breadth first search. And then we will see how these 2 algorithms can be applied to directed graph. Okay, so let's see the definition of spanning trees. If G is a simple graph, then a spanning tree of G is a subgraph of G that is a tree containing every vertex of G. So let's see this example, because we can see this example G is a simple graph, but we have a lot of circuits, right? A, B, F, E is a circuit. E, F, G, E is a circuit. And we also have the triangle C, F, G is a circuit. So in this case, it's not a tree. Okay, so if G is a simple graph, maybe it contains circuits or not. But the definition for the spanning tree is a subgraph of G that is a tree and contains every vertex of G. So how to make this graph to be a tree, contain every vertex in this graph? That will be the definition of spanning tree. Okay, so if you discover the secret of a spanning tree, that means we need to break or remove the simple surface from the graph while we maintain all vertices within this tree. Then we can create a spanning tree. So in this case, if we have 3 simple circuits, the first step is to remove the edge A. Then we can make A, B, E, F, A. This simple circuit something as we remove edge A, B. Alright, and then we still have the simple circuits here. So how about remove edge E, F? In this case, we have the simple circuit already right here. Now, it's not exist anymore. And lastly, CFGC is a circuit. If we remove the H,
this graph is a subgraph of the graph G, and this graph is a tree, and this graph contains every vertex of the graph G. So that's how we create a simple tree. All right. So based on this example, we can have the first theorem for spanning tree. A simple graph is connected if and only if it has a spanning tree. Okay. So firstly, let's see the direction from right to left. If it is a spanning tree, then the graph is connected. All right. So this is very easy, right? Because we already know if the graph is a tree, that means we can discover a path between any of the vertices of the graph. So if you can discover any path of any two given vertices of the graph, then this graph is connected. Okay, so if the given condition is if it's already a spanning tree, then it is a very strong condition. All right. Then let's see how we prove by from left to right. Uh, Given a simple graph connected, how to prove it has a spanning tree? All right. So we can see if this simple graph is already a tree, then of course the graph itself is a spanning tree of the graph. But if the simple graph contains simple circuits, then we need to prove that it has a spanning tree. Then we can apply the similar operations of our previous example. We can remove edges from a circuit. A circuit means you can visit, for example, the vertex V1 to Vn by two different paths, right? So once you remove one edge to break the path, that still make V1 to Vn connected. Because originally there is a simple circuit here. That means V1 can visit Vn by two different paths. Once you remove one edge, then you just break one path. It's still connected. Alright? And then we can discover the next circuit and remove an edge until we cannot discover any simple circuits. Then we will make a simple connected line to give this tree. Alright? So the proof is very easy. Next, let's see the first algorithm to help us to discover the spanning tree is depth first search. Okay, so let's see this example, how we discover the spanning tree if we consider how to discover or construct a very, very long path. Okay, so we call this depth first search. If we select a random vertex or arbitrarily chosen vertex f, for example, the first vertex we choose f here. And then we try to build a path as long as possible. Okay, for example, if we start from f, we can g, h, k, j, then that will be one possible path starting from f. And then that's the longest path we can visit. And then once we go to the end of the vertex, then we cannot visit any more new vertex. Then we go back to the previous vertex to see if we can create another path. In this case, if we go from j back to k, then we don't have any chance. So we go back to h. So once we go back to h, then we can discover there is the vertex I we haven't visited yet. Okay, and then we can create a path from h to I, and then we go back I to h to g to f. Once we go back to f, then we can visit d, e, c, b. And then if b we cannot visit any vertex anymore, then we go back to the previous vertex c. Then we can visit h. just create that first tree by this algorithm. So let's see the following figures. If we visit graph F, then F, G, H, and J is the first pass we visit as long as possible. And then we go back to H and create another node I. And then we go back to F, create another pass D, E, C, A. Okay, D, E, C, A. Okay. Once we go to A, then we go back to C and visit the last vertex C. So in the end, this figure is just a simple tree we visit by depth first search. Okay, so the concept is very easy. Visit as big as you can. If you cannot visit anymore, then go back to previous vertex to see if you have any other new rows you can put in the past. All right, so the algorithm of depth search is very simple. First step to form a fast starting at a given or randomly chosen vertex in this graph. And then we successfully add vertices along the path as long as possible. If we cannot go any further, then we go back to previous vertices in the past to see if we can form any new paths until we visit all vertices in this graph. Then that's going to be the end of the algorithm. All right. So for this algorithm, we can see, go back to our previous example, we first visit F, G, and J. So if we want all paths or all edges to visit as blue edges, then this blue edges is called tree edges because it contains in tree. And then we have two edges, E and F and F to H. Or we call this back edges. Because you can see, once you create the path F, D, E, C, A, then the H connect E to F. Actually, it connects the descendant to ancestor along this path. Okay. So similarly, if you consider F, G, H, A, J, then this H, F also connect the descendant to the ancestor along the path. Okay, so for such kind of edge, we call them back edges. Maybe you will see more algorithm to discover the path of the simple graph using the back edge and depth first search. So that will be another story. All right, so next, let's see the algorithm of depth first search algorithm. We call this DFS. So the input is connected graph G with vertex we want you to create. All right, and then the first step is to create a tree. Okay, it contains only one vertex A1, B1. Okay, so actually you don't have to visit starting from B1, you can start from any vertex. But in this case, we call the first vertex we visit B1. And then we visit B1. So B1 is another procedure. Then we can apply a recursive call to visit the procedure visit. Okay, so if we consider B1 as the vertex F in our previous example, once we select B1 as the starting vertex, then let's see what is the procedure visit. Okay, the input is the vertex of the graph. So in this case, it will be the vertex F in our previous example. And we have a for loop here for each vertex W adjacent to B and not yet in the tree T. And then
in this for loop, we add the vertex W and the HVW to T, and then we visit W. So you can choose any adjacent vertex to V1. So in our previous example, we visit FG, right? So in this case, we choose G as our adjacent vertex, and then we add G and the HFG to the tree. Okay, so we create something like this. So initially we have F, and then we select the vertex G, and then we add HFG into the tree, and then we apply a recursive call procedure visit using the input of G. Okay, once G is the input, then by the procedure of visit, we can select any vertex that adjacent to G, okay, and add H and GH into the tree, and then we recursively call the procedure visit using the input H. Okay, so in this case, you can see once you apply the recursive call for visit, you can visit GHKJ until there is no adjacent vertex to J, then it goes back to the previous recursive call. All right? So let's write down your answer for this example to apply first step search to produce a spanning tree if we choose A as the root. All right, actually by the given algorithm, you can see the spanning tree when we apply depth first search is not unique. Okay, maybe every student has your own answer. The answer is not unique. Okay, so let's see. Who want to share your answer? Okay, please. Please write down your spanning tree on the blackboard. Yeah. Please, write, not to the back of the screen. All right. So let's see how to examine if this is the correct spanning tree by depth versus algorithm. Okay, maybe we can consider our procedure or algorithm. If A is the input, then it goes A to C, C to D, D to E, H, I. Okay, so that will be the longest path, our first choice. So then we need to go back from I to H, right? So in this case, we don't have any. In his answer, there is no other vertex attached to H. So maybe it's not this sequence. Maybe let's try A, C, D, F, G, J. Okay, so if we have the last vertex J, that means when we go back to G, we need to go from G to other vertex. So this is not the answer derived by first depth search. This is spanning tree, of course, but this tree is not derived by first depth search algorithm. All right, so anyone? Okay. Maybe you like upper. Okay, thank you. So let's verify. How about this answer? A, B, C, D. Okay, A, B, C, D, and F, G, I, and F, G, I, or F, G, J, right? So A, B, C, D, F, G, J, and we visit last vertex. Then we go back to the previous vertex G to see if we have any possible new paths. So G can go to HI. Once it go to HI, then I will be the last vertex we can possibly visit. So we go back to H. And when we go back to H, we have another possibility because we still can visit E. So in this case, once we visit E, that will be the last vertex in this graph. So we finish the tree just like this. Okay, so can you distinguish the difference between your answer to it? Okay, very good. Let's see another algorithm, breadth first search. Okay, so let's see for this graph, if we apply breadth first search algorithm to discover the spanning tree, so the first step is to arbitrarily choose a vertex. In this case, we choose E as our starting vertex. Okay, and then to build the spanning tree, we discover all possible vertices adjacent to E. Okay, so in this case, we can visit B, E, F, I, because these four vertices are adjacent to the vertex E. So in this case, we build a tree like this. E, then we can visit B, E, and I. All right, and then for these four vertices, and then we expand our spanning tree from these four vertices. For example, B can visit A and C. Okay, so B can visit A and C. And for D, we can visit H because A is already visited. So for starting from B, we can visit H. And then for F, we can visit J, and for E, for I, we can visit K. So in this case, you can see once we consider as breadth as possible, then at first level, we can visit four vertices, E, and I. And then for the next level, we can further expand from our previous E and I to other vertices, A, C, H, G, and K. And in the end, you can visit A to see, because we already have B and D in our tree, so A cannot visit any more vertices. However, G and K can visit more than E in this case. So you can see it's just like the flood, right? It can, the water can flow by different directions as fast as possible. Okay, so that's the reason we call this breadth first search. All right, so let's see the step of this algorithm. We first arbitrarily choose a root of any vertex of the graph, and then we add all edges to this vertex to other endpoint we call level 1. And based on the vertex of level 1, we add the edges to other points of level 1, which is not included in our previous tree. And then we can extend on level 1, level 2, level 3 until there is no more vertex we can include it. And that will be the end of the algorithm. Okay, so next let's see the depth first search algorithm. We call this BFS. Okay, the input is the same, the given graph G with vertex V1, V2 to Vn. And then in this algorithm, we maintain two data structures. The first one is the tree T. Okay, originally the tree T only contains the starting vertex V1. And then we maintain an empty list L. Okay, so this empty list L is very important because next week we will see how we use this infrastructure in the while loop. Okay, so our first starting point is V1. So we put V1 into the list L. That means we maintain the list of unprocessed vertices. So we need to expand from the vertex in the list L. Okay, so our while loop is when L is not empty, then we remove the first vertex V from the list L. Because we are trying to process this vertex V. Okay, so we can remove from the list we already processed in the next step. Okay, once V is removed from the list, then we can consider for each neighbor W of V. Okay, if V is not in L and not in T, then we add W to the end of the list, and then we add W and the HVW to T. Okay, so maybe we can try a little bit of this algorithm. Okay, if our starting point is E, and then initially our tree only contains the vertex E, all right? And then let's see our algorithm. We maintain the list L, so in this case, we put the vertex E into L. And when we enter the while loop, when L is not empty, because currently we have the vertex E in L, and then we remove the vertex E from L. And for the while loop, we consider for each neighbor W of if it is not in L and not in T, then we add W to the end of the list. Okay, so let's see. We have P is adjacent to E. So now we have L. Okay, so we can add B into the list. And then we add B and HEB into the tree. Okay, and then we also have the vertex D. So we add BD into the list L. And then create the vertex D and add the HED, and then F and I. Okay, so now in our list, we have BDFI in our list. And then we create the tree by this 4 vertices. Okay, so next, let's see. Once we process the first vertex, and then
we go back from the beginning of the while loop. Currently, L is not empty, so we remove the first vertex. So in this case, our list we have B, so we remove the vertex B. Then we consider the neighbor of B. Okay, so let's see. Neighbor of B, actually we have A and C. Okay, so we add A into the list, and then we build BA into the tree. And then we have the vertex C, so we put C into the list, and then we build the vertex and HBC. Okay, so there's one thing very important because once you consider the neighbor B and C of the vertex B, you need to check the vertex is not in L and not in P, then you can add into this. And because for next vertex, once we consider B, then in the next iteration, we remove D, right? So now we have the adjacent vertex to B. Actually, it's AEH. But if you consider the neighboring vertex AEH, we know A and E is already in the tree, and A is also in the list. So you cannot add A and E into the list L. You can also add H. Okay, so in this case, we add H into the list and add DH into the tree. Okay, so you can see first, this algorithm is very interesting because based on the data structure, tree T and the list L, we can apply, we can make the first search of article. All right, I hope you can trace this algorithm by yourself, how to build a tree if you follow the set of the algorithm BFS. Next, let's see what happens when we apply depth first search or a breadth first search into the directed graph. All right, so let's see the conclusion first. The results is not necessarily a spanning tree, but maybe we will have a spanning forest. Okay, so let's see. If we apply DFS starting from A, okay, and then we can go to A, B, C, G, all right? Once we go to G, then for these directions, it's all point to G. So that will be the last vertex. And then we go back to C, and we cannot go here, so we go back to B. From B, we can also visit F and E. Okay, so in this case, we visit F and E. And then for E, this is the endpoint. For F, we have nowhere to go. Okay, so in this case, you can only build the spanning tree like this. Now we have to visit all possible paths for if we start from vertex A. If we have nowhere to go, but we still have other vertices we haven't visited yet, then we can choose another vertex to form a new path. In this case, if we choose P, then you can also visit PHL and then that will be the longest path we can visit. And we have last vertex I. In this case, we have three different directed graphs. So we call this a spanning forest. Because we cannot have one single spanning tree. Instead, you have three different directed trees. So we have a spanning forest. All right,
So you can see actually DFS and BFS can also apply to the right-handed graph. We just have different results from simple graph. All right, any question for this algorithm and the way to build the spanning tree? All right, then we go to the last section, minimum spanning tree. We will introduce two different algorithms to help us to build not only a spanning tree, but we build a minimum spanning tree. So minimum spanning tree means we construct the spanning tree in a graph where we have weight for the edge. So we call this weight graph because we have numbers of weight among all edges. So how to create a spanning tree when we calculate all this weight along the edge, the number is minimal. Okay, so we call this a minimum spanning tree. It has the smallest possible sum of weights of its edge. Okay, and then we have two algorithms, Prim's algorithm and Crossco's algorithm. So firstly, let's see the concept of Prim's algorithm. If we want to build the minimum spanning tree, then we can choose an edge with okay, because we hope the total number will be a minimal number. So you choose the first choice is to choose the smallest number. Okay. So choose H with least weight and include in the spanning tree. And then we can select the edge of the least weight that is incident with the vertex in the tree. Okay, and then if it is not create a cycle, then we can include in the tree T. Otherwise, we discard it and we repeat these two steps. All right, so maybe we can see this example. Once we have this graph K5, and we have a weight along each edge. So the first step is to choose the edge with least weight. So in this case, you can see we have 7, 10, 11, 12, 10, 13, 15, and 16. So the list of the edge with least weight will be the edge AB, and the weight will be 7. Okay. So our first step is to choose the edge AB with the weight 7 into the spanning tree. And now we have the spanning tree with two vertices and the weight is 7. Next, we need to choose any vertices and edges stemming from the current tree. Okay, so now we have two vertices A and B. So let's see what is the least weight we can choose. From A, we can have 10, 12, and 16. From B, we can have 13, 10, and 16. So in this situation, the least weight we can choose is 10, right? You can choose AB because the weight is 10. You can also choose BD because the weight is also 10. In this case, you can choose either one because it gives you the same weight of the edge. So in this case, if we choose AB, then our second step, which is the edge AB with weight 10, so our current spanning tree will be BAD. Right? And then for our current tree, then we can select next least weight. Okay, so B, we can choose 13, 10, and 16. For A, we can choose 12 and 16. For B, we can choose 10, 13, and 10, and 10 we choose. So we have 15. So in this case, the edge with least weight is 10. But
then it gives a cycle in this graph. Okay. So if you choose the H and form a circuit, then you cannot choose the H. So we cannot choose BE in this case. However, we can choose the next a little bit larger weight, BE, with the weight 11 into the tree. Okay, so in this case, we choose BE into the tree. Now we have A, B, D, E in our spanning tree. So next, let's see. The next weight we can choose actually is 12, right? Because we cannot choose this 10, and we already choose 7, 10, and 11. So next we can choose, we have two different choices, 12, A, E, and E, C. So we cannot choose A, E, right? Because if you choose A, E, then you will follow the cycle. So we have only one choice to choose E, C. So once you choose E, C, you just add the H into the tree with the H weight is 12. Then you can see actually we have included all vertices A, B, C, D, E into the same tree. And then we just keep the total weight to be minimal as possible in each step. So you can see actually this is another greedy algorithm. We choose the least weight in each step and hope the total weight will be the minimum. So that will be the final answer of the minimal spanning tree from Prime's algorithm. Okay, so you can see the prime algorithm is very easy. Once we have G as our input with n vertices, then we just maintain a big structure a minimal weight with minimal age. Then we can apply this for loop, and we choose the HE with minimal weight instead with the current vertex in P, and not for a simple circuit. If it is true, then we add this H into the tree P. Then we apply to next iteration. All right, this is another example when we apply Prime's algorithm. So you can see in this figure, we have a lot of different cities, San Francisco, Denver, and Atlanta. And then we have the airplane fare for each route between two cities. Okay, so to form a spanning tree, so we can choose the H with least values. In this case, we just choose Chicago to Atlanta because the airplane fare is 700. Okay, so we choose Chicago and Atlanta into our spanning tree. And then you can start from Atlanta to other cities and Chicago to other cities. And what is the minimum age you can choose? From Atlanta, we have 800, we have 1400, and we have 200. From Chicago, we have 1200, 1300, and 1000. Okay, so in this case, our minimum choice will be 800. So we include the H Atlanta to New York in the second step. The cost is 800. Now we have the city Chicago, Atlanta, and New York. We can further consider what are those agents attaching to the different cities with the minimum cost. So that will be in Chicago to San Francisco, it will be 1200. And last we choose Chicago to Denver, it will be 900. So on the tree behind these two edges, that will be the minimum spanning tree for this graph. All right, lastly, let's see another algorithm, a cross-cost algorithm. So maybe we can see the example first.
Okay, maybe we see the step first. We arrange all edges in the graph in increasing order, and then we choose one edge with the minimal weight, and then we insert this edge in the current spanning tree. We add the edge and of the least weight to D. If it does not create a cycle, then it is a measurable edge. And we add to D. Otherwise, we discard it and we repeat step 4 and 5. So by the step of the algorithm, you can see it's a little bit similar to Prime's algorithm, right? But the difference is for Prime's algorithm, we just choose the edges incident with the vertex in P. Then you can expand a new edge from the current stage to P. But in Kruskal's algorithm, actually we just choose the minimum edge. You don't have to incident with the current stage to P. You just choose all from all possible candidates and choose the minimum edge. All right, so let's see this example. All right, if we have a graph like this, actually you can order all weight of edge because we have 1, 1, 1, and we have 2, 2, 2, and we have 3, 3, 3, 3, 3, 3, 3, and we have 4, 4. That will be all weight of this edge. So we choose from the edge with minimum values. If firstly we choose CD into the spanning tree with the weight 1, and then we can choose next edge with KL because it's also 1. So you can see once you choose CD and KL, it's not connected. Right? Because in Kruskal's algorithm, we just need to make sure we don't have to cycle into the current spanning tree. So next, we choose another weight 1, BF. Okay, so once BF is included in the spanning tree, we don't have any cycle. And then, so in this case, you can see we have choose all edges with the weight 1, right? So next, we can choose the edge with the weight 2. So in this case, we choose CG because the weight is 2. And then we choose AB, and then we choose FJ. Okay, so currently we have choose all edges of this weight 2 into the spanning tree. All right, next let's see. Next edge we include is BC, the weight is 3, and then JK, and JK is here. So once we include JK, you can see we don't have any cycle. Okay, so JK is okay. And then we have GH. Okay. So next we have IJ. Okay, so currently you can see we have almost included all edges with 3. But now we still have AE and FG. But we cannot choose FG, right? Because once you choose FG, then we form a cycle. So we can only choose AE. Okay, once we choose AE, then that will be the end of the algorithm because we have included all vertices into the spanning tree. So that will be the end. And we can calculate the total weight to be 24. All right, we have only 1 minute left. So I hope you can practice this example by yourself because you will see this question in the final examination. And lastly, we have homework assignment for you, but here we leave it as a practice. You don't have to hang in your answer because on Thursday that will be our final examination. So I will ask A to release the instrument of this exercise for you, and maybe you can practice a little bit. Because just like the midterm examination, we will choose like 2 or 3 questions from our whole assignment into the final exam. So I hope you can practice this by yourself because definitely you will see this again. Alright， 好，那看看同学们有没有什么问题？今天应该就是我们这学期最后一堂课了。好，同学们对于期末考或是作业或成绩计算有没有任何问题？有问题吗？OK， 只要没问题的话 ，Good luck to your final examination。